So they found out that, yes, so you extract energy out of the bottom in the Bay of Fundy so that your tides there are going to decrease, but they are going to increase into the Gulf of Maine, right? So that, that leads us, right, to ask a few hard questions. If you're interested, right, in characterizing bottom friction, well, it's good to have a picture of the bottom friction. So this is an example of what it would look like. This is a submarine photography, right, of Minas Basin, where the tides are the highest here. But that raises these questions. Okay, where is the level at which we can see that indeed somewhere, right, the bottom or inside that layer, where is it that we have the zero slip condition to crank up a proper hydrodynamic model? My answer to that is a good question. It's pretty hard to say, and there's different opinion, different approaches that have been tried every which way, right? Now, the sea bottom interest also, well, it depends on where you are. There's a large variability here. So what kind of modeling can you do? So I'm suggesting first, in such complex system, to first look at the phenomenological models, right? And also it's been realized, right, not that long ago by hydrogeologists that they are, in the underneath the bottom of the system, there are several aquifers that resulted, right, from the melting of the retracting glaciers, right, and then burying by sediment. So there's a lot of aquifers, right, underneath the Bay of Fundy itself, right. So with this in mind, right, so I came up with this model here, this boundary layer model, and I call it a geophysical viewpoint because the constraint on the properties of the layers that I use in my modeling, right, come from geophysical measurement here. So basically the bottom is rough, right? And as the tide comes in or comes out, right, you will have a direct elastic response, right, represented by the springs, right? But there will be a delay, a rebounding until the next instant of equilibrium is reached, right? So to answer where is the zero slab, it would be associated with the skin depth, right, of the deformation control, right, by the properties of the rock bottom formation here. So this is calculable with a well-known theory of elasticity here. So we can come up with a parameter to examine, okay, the amount of energy absorption, dissipation that occurs as the tides are sloshing back and forth through the system here, right? So in order to calculate this dissipation factor, right, you need to actually come up with a mechanism that absorbs energy to calculate the delta E, and the E itself, well, that comes from the theory of elasticity. So these are known equations here. So the mechanism, right, involves, right, a grain-to-grain interaction. So the grain shown there in that column of representative model rock are rough, right? And that the fluid, the blue stuff, is a fluid that is viscous. So has some of the pores closed, other ones are open, so that permits a pressure gradient to be set up, and that mini fluid, right, is sloshing back and forth and absorbing energy, right? So in order to structure my porous medium, permeable medium here, this is the top view, say at the bottom rock part, right, and I introduce a characteristic scale, crack, right, in which the absorption occurs, right? In cross-section, we have different orientation, again, to favor the flow back and forth, and so increase the amount of dissipation. 3 minutes, okay. So, hey, do you want to go through these equations? Can I have extra time? Okay. No, so at the end of the day, when all the dust falls down, okay, the calculations are done, right? I obtained these Q curve, right? One of the Q curve, and there is a maximum, right, around, right, the natural period of the system itself, right? So then I have calculated that with realistic values, as realistic as possible, and I have calculated the power dissipated this way. And I get basically for the numbers that were calculated by Pelling and others, right? They're kind of the same amount of energy extracted, right? So that mechanism can be as efficient as installing these turbines, right? And you have to keep in mind that you're looking over a change of 100 years. And during that time, the bottom of the bay is subjected to all kinds of perturbation. Hurricanes going through, right? The fatigue, right, of having 100 years of sloshing back and forth, earthquakes, right, that would disturb the perturbation itself. So if we could use this mechanism here to actually explain at least part, right, of the fluctuation of the M2 tide. All right.
Thank you. Do we have any questions? David.
Oh my, it's David Greenberg.
Surprise. Just a couple of points. One is what you're describing is very important for the models and modelers. Some of that has been tried with Yongsheng Wu, where he took probably the same data that Gordon Fader had with that picture. And that picture is probably minus passage. As you get into minus basin, there's a gradation from that all the way to very soft mud around the edges and at the end. So yeah. There is that. What Yongsheng did was he took the bottom roughness as indicated from the GSC type maps that they had, put that into the 3D high resolution FVCOM model, and was able to, for the only time I've seen a very good representation of the vertical velocity from an ADCP in minus passage, where essentially the boundary layer goes all the way 100 meters to the top. Yeah. And anyway, so they did a very good representation of that with that model. And also what you were talking about at the very beginning has been addressed by somebody named Greenberg and a bunch of people.
Yes.
Where we did, it's in atmosphere ocean, somewhere around 2012, 2013, and yes. I've got the reference here if you want it, where they did an isostatic rebound was a very, very important part of that.
It is a centimeter level, the elastic.
And more important is the unknown guesses we made all the way out to the shelf break, and I touched on that in a question in another talk. So anyway, so that's a little bit.
I had enough slide, but I was going to bring up your contribution to the SWOT, the SWOT, modeling and how to correct tides from the SWOT data, right? But your reference to including roughness, right? The actual rheology of the bottom is still solid. The bottom, the roughness can alter, right, by the work of that you quoted. Right?
Yeah.
But the actual state of the rock, it's still a solid.
Okay, yeah.
Okay, well, I'm going brave. I'm including elasticity, because the bay deforms. We've measured it.
Yeah.
Right,
yeah.
and then in an earlier thought I showed that the deformation, the tilt meters and the displacement are even more now because the tides are.
Well, we know the topography there is dynamic. I mean,
yes.
Sorry.
Okay. Well, thank you. It's well.
I think we'll continue this conversation offline. Let's thank the speaker again for an interesting presentation. Our next talk is online. We have Michael Casey from DFO, who's going to be talking about driving processes and associated variations of physical environmental conditions in the St. Anne's Bank Marine Protected Area. One second while we get the slides up. We've still got the previous one showing. Oh, we have to.
Hello, who's speaking?
Hi, Mike. This is on the volunteer here at CMOS. Also, we have to and to the person we'll put it on the mic now. Can you see this screen? Yeah.
So yeah, just have them speak through.
Okay, yeah. Now you can. I think you can just start speaking now.
Okay, just I need to reposition myself so I can see my clock. That was on my phone. Okay, I'm ready if you are.
Could you like make your screen make your screen like the presentation mode because we have it on small display.
I have it on presentation mode.
Yeah, we only have the slide. We don't have your presentation view here. We only have like the slides.
Oh, okay.
Could you share could you share the whole window instead of only like the presentation? Yeah.
Okay.
I think you need to share the entire screen.
The entire screen.
Yeah, you need to share the entire screen.
And up to display all your opening windows. You control alt and up on the keyboard. Yeah, so you display all the windows open then just the slideshow.
There we go.
You need to share
Yeah.
the entire screen.
You just
Are
share
you
it.
sharing your screen from the what's the up from the side?
Yeah, I'm sharing it from the site.
So and now you can see your PowerPoint window. So you need to capture
Sometimes
the
it's hard to
slideshow.
share the entire screen. You just share
Yeah,
the
for some
one.
reason I'm not doing that. I have it in full screen mode, the presentation mode. I can do it right now.
And are you sharing the entire screen or you just capture the
Well, maybe that's what we need to do. We'll try something else here. Maybe if I stop sharing, then we can try.
Yeah.
so capture the entire
Stop sharing and share the entire screen.
Let's see. How was that?
And it was a couple of seconds.
There's a bit of a delay.
Yeah. No, it's full.
Yeah,
we can see.
it's good.
Thank you, Mike.
Is that good?
Yeah, that works.
Yes, that works.
Okay. Let's see if I can do this. Okay. So I'm going to be talking today about the driving processes and variations of physical environment conditions on St. Anne's Bank Marine Protected Area. This is work I've been doing with Hui Shen and others at the Bedford Institute of Oceanography. So we'll be looking at the St. Anne's Marine Protected Area, which is this green area off the southeastern Scotian Shelf between Cape Breton Island and the Laurentian Channel. The MPA was established in June of 2017 as the largest annual temperature range on the Scotian Shelf. It's home to many permanent and transitory migratory marine species. The DFO is tasked with monitoring the health of the MPAs through such things as the MPA monitoring framework that we're trying to set up. And we need to assess the changing environmental conditions on different timescales. And we need to be aware of how this impacts the marine protected areas, the marine life. And for doing this, I'm using the GORS 12 ocean model reanalysis product from CMOS, which is a 1/12 degree resolution with 50 vertical levels from 1993 to almost present day, and daily and monthly averages. And we're using this as a test bed for the digital twin of the ocean project at DFO, which will hopefully feed back into the MPA monitoring framework. So the St. Anne's Bank is located here on the Scotia Shelf. And the main water sources are water from the western Gulf of St. Lawrence that goes around Cape Breton through the Cabot Strait onto through the MPA and onto the Scotian Shelf. And also the deeper layers of the Laurentian Channel, we have water from the Laurentian Channel going back and forth there. And surface, we have water from the Newfoundland Shelf and the eastern Gulf of St. Lawrence coming down through the Cabot Strait and what have you onto the MPA, causing some interesting fluctuations. So let's look at the surface climatology to give you an idea of what's going on. So in the top row is 6 color bars and it has currents attached to it. The same information is on the bottom row, but with individual contours for each one, so you can see the variations across the field. So in March, the MPA reaches its minimum temperature. And if you look at the temperature and salinity gradients across the field, from the west to east, you have colder temperatures in the west and warmer temperatures in the east, although the actual range is very small overall. The salinity is also fresher, closer to the coast, to the west, and more saline in the east. And that will hold throughout the whole year, regardless of the season. However, as you're moving towards June, and what we see is a warming of the surface area, and you see the temperature contour flips sign essentially. So it's now warmer in the west and cooler in the east, whereas the salinity is still pretty good. As you head towards September, it reaches maximum temperature around September, and you also see that flipping contour there, or it's still warm in the west and cooler a little bit in the east. And in December, as it's cooling down towards minimum later on, you see that it's a little bit more complicated. It's back and forth along St. Anne's Bank there. Let's see here. So what else we can do here is run a transect along the St. Anne's Bank line here that's parallel to the AZMP line. Stations 1 through 5 are within the MPA. And if we look at this here, don't worry about the current. That's these columns here. But March up here in the upper right-hand corner, June, September, December. If you look at the various months, you see that the areas of the MPA that are within, that are bordering the Laurentian Channel do not have much of a seasonal cycle at all, whereas the surface layers, of course, have a seasonal cycle. The dividing line is approximately at 100 meters. Above that, you have a seasonal cycle. Below that, you have much of one at all. You can see the development of the intermediate cold layer at the various in the summer and spring and summer and fall, and then dissipation of it as it cools back into the winter. So we can take advantage of the fact that if you look at the slope of the Scotian Shelf, the edge of the MPA, that we can create depth-specific average bottom conditions and climatologies for the various spots on the bottom of the MPA, so that we can have a better idea of how the surface of the bottom is varying with respect to time. We're taking advantage of the shallower in the west and deeper in the east. If you look at climatologies on bottom conditions, you see that once again, here's the seasonal cycle in terms of a temperature salinity diagram. That below about 100 meters, there isn't much of a seasonal cycle. Above, shallower than 100 meters, then there is a substantial seasonal cycle. And so what I did was I looked at the bottom conditions and from those and calculated anomalies for depths down to 100 meters, and then I did another one for depths deeper than 100 meters. And what you can see is lots of interannual variability, but for below 100 meters depth, it's up and down and lots of variability, both in the short and the long-term scale. But there isn't much of a long-term trend below 100 meters. But obviously, for shallower than 100 meters. But for deeper than 100 meters, we've got a bit of a trend here, particularly from about 2010 onwards. There seems to be a continuous trend in temperature there in terms of anomalies, from about -1 or maybe a little better to about +2. And that's mainly sampling the Laurentian channel water. So something is happening in the Laurentian channel water for a slight increase in the temperatures, but significant. So what are we getting for variability on those shorter time scales? That's telling us what the longer time scales. What about the shorter time scales? Well, let's look at St. Anne's Bank AZMP Station 1, which is the station that's closest to Cape Breton. There's no observations here, but this is just a couple years of variability. And what we see is at different layers, 0.5 down to about 55 meters, a very shallow area. You see the spring, summer surface heating and stratification happening, and you get fall cooling and mixing into winter along here. And it varies, the shape of it varies from year to year, but the overall effect is the same each year. At Station 5, which is right at the edge of the Laurentian Channel, you see that the lower layers indeed have not much of a seasonal cycle, and but the upper layers definitely do have a seasonal cycle. But what are all these lumps and bumps that we're seeing in these signals, the shorter term stuff? Well, for example, here, this one here happens to be Hurricane Dorian. So you see that surface layers are getting cooler, and the deeper layers, deeper being as low as 25 meters, are getting warmer. And so what's happening is Hurricane Dorian is coming along and seems to be doing some wind-induced mixing. Whereas these other lumps and bumps here on the curve are more from short-term variations, several days and months alternating between different parcels of water. And I'll highlight that in a minute. But first, as an example, Hurricane Dorian blasted through Halifax on September 7th, and then it went into the Gulf of St. Lawrence, causing all kinds of chaos in different places. And if you look in the upper left-hand corner here, before September 6th, before the hurricane hit, the surface temperatures were fairly warm. Go to a couple days later, and you see that there's been a substantial decrease in the surface temperatures from the passage of the hurricane. Was there evidence in any observations? A tiny bit here at some deeper stations, but otherwise, most of the moorings that were out there at the time were too deep to capture what was going on. But the other short-term variations that we're seeing are basically alternating parcels of water coming down from the competing parcels from the Western Gulf and the Eastern Gulf, St. Lawrence, coming through the Cabot Strait. You see these different blobs. If you watch them in animation, they sort of flow down a bit in a chaotic sort of fashion. But it's basically the fresher Western alternating with saltier Eastern water masses. And you can see it particularly in the salinity versus the temperature, where you can see it there as well. So that's a summary of variability, but let's move on. I won't go through all that in all the details, but what does this mean for habitat suitability? So, these temperatures are evolving. How is that evolution how is the MPA changing in terms of its suitability for various species to inhabit that MPA? Well, earlier this year, this paper was published by some colleagues, and within that paper, they compiled a list of species-specific temperature and depth ranges preferences. So we can use these and apply them to the St. Anne's Bank MPA to see if these long-term changes or short-term even are affecting what these species think of this as a good place to live. So here's a mudfish temperature range. It likes temperatures between about 6 and 19 degrees, 18 degrees. Depth range 61 to 352 meters. So this would be, it's a benthic fish, so you want to look at the bottom area fraction that's contained within these parameters. And as you can see, this blue means it's too cold for the fish. Suitable means thumbs up, it likes it. So as you can see at the beginning of this temperature time series, it was blue, and it doesn't like it. But as time goes on, the temperature goes up, and you might expect this fish to move into this area if it's so inclined. Similar for a white hake down here, which is pelagic fish. So you want to look at the total volume of the place available to it. You see a similar time series. It's liking this better and more as temperatures warm. On the other hand, we have deep water redfish, which is benthopelagic fish. So you want to look at volume. And in this case, for the most part, in the earlier years of the time series, it was a nice temperature. It was green. However, as time has gone on and it's warmed, it doesn't like the warm temperatures. So you see that the warm temperatures are it's becoming less and less suitable for this fish. So that's basically the end of it. The long-term consequences of temperature changes in the MPA have consequences for some species. Impacts need to be investigated. Will some leave? Will some arrive? There's only one input into our MPA monitoring framework, and more work is needed. Thanks for your attention. That was reasonably coherent after all the technical difficulties. Thanks.
We have time for one very quick question if someone has a quick one. If not, let's thank Michael again for his interesting talk and be willing to deal with all the technical issues. Our next talk is in person. It's going to be given by Susan Allen from UBC, who's going to be talking about connectivity across the border in the Salish Sea, fluxes, river water, and plastics.
It's not very often I get to pick the microphone and move it up.
Yeah, go ahead.
Thank you, everyone, for being here. I'm excited to actually be giving this presentation in person. So this is a piece of work that's basically pulling together some results from my co-authors and putting it together in a slightly different way to answer a slightly different question. And so what I want to, sorry, I don't know where my opening slide. Oh, I want the next slide. I'm missing a slide. How can I be missing a slide? Okay, that's okay. I know I'm missing my title slide. That's okay. I have 3 co-authors and you'll see them later. So that's okay. So here we'll start with this one. And so what you can see here, this is the Salish Sea. And it's the body of water that lies between Vancouver Island and Canada and the US. And it has this red line that runs through it. And of course, no, the water doesn't care about the border, but there are various reasons why the border matters. First of all, when we go to sea and we measure things in our own waters generally. It takes a lot of paperwork to measure south of the border. And so many of the older studies looked at one side or the other. But of course, we're also interested in it because politically, things that are put in the water on one side go to the other side, but they have different political jurisdictions, and different chemicals, for example, are restricted differently on the 2 sides of the border. So I'll talk a bit more introduction. I'll talk a little bit about the modeling, because all of these are modeling studies, and then I'll focus mostly on the results, and then I'll pull it all together at the end. The more details are actually where you can find the details from my co-authors. Okay, so the Salish Sea is a semi-enclosed marginal sea, and it's actually quite nicely enclosed. So the opening up at the north there is 4 kilometers across. And then down at the south, that's the main entrance to the Pacific Ocean at the mouth of Juan de Fuca. There's a very strong freshwater influence, another way to say it rains a lot. And the Fraser River is the largest, and those blue circles are showing you the river water coming in November 2023. And the biggest circle is the Fraser River, representing the most flux. But it's not by any means the only river coming in, and in particular, there are 4 large rivers coming into the north end of Puget Sound, which you can see towards the south end of the picture. There's also what the field is you're looking at is salinity, where the greens are less salt water and the browns are more salt water. And there's a couple of regions where we have really large tidal mixing. One of them is in that Harrow Strait Gulf Islands region. Another is at the north end of Puget Sound. And the last one is up near the top there, Discovery Passage, Johnstone Strait. And so those are 3 large tidal mixing areas. And we also have reasonably large populations who live around here. So Vancouver is just north of the mouth of the Fraser River. And just where the symbol saying Puget Sound is, that's Seattle, Tacoma. Okay, so if we think about just general estuarine circulation, I want you to start on the top right there. That's our classic sketch where we have near surface water going from the right, which would be where the river was, out towards the ocean. And then near the bottom, the darker blue water representing slightly more dense water. We have water coming in from the ocean and heading towards the river. We also have estuarine mixing going on. So some of the water that comes in from the deep, from the Pacific, say, is mixed up into the surface layer and goes back out. We call that the efflux. And also some of the water that's coming from the fresher basin is mixed down into the salt water and leaves. Of course, the real world is more complicated than this. So let's now jump to the picture on the left, which is a surface picture, a map of that Gulf Island, San Juan Island mixing region. Note the red line. That line is called the Thalweg. It is the deepest line through this system, and we use that to look at the sideways picture of the model. Okay, so it's squiggly, not straight, but it basically gives us a picture very similar to the sketch we had. And so on the bottom right, I'm showing you a 1-hour snapshot of the salinity field along that squiggly line. And I've kind of put the same arrows on top of it. So we have water sort of near the surface. I mean, it's actually 3-dimensional, going from the Strait of Georgia out to Juan de Fuca. We have Pacific water coming in, and we have a considerable amount of efflux and reflux going on in that system too. And so that's the estuarine flow driven by the Fraser River, which is a very Canadian picture. But there's also the American picture, and this one I'm just pulling out of quite a established paper from 1980. And here they're running their Thalweg from the Pacific Ocean into Puget Sound and down through Puget Sound. And they have their sketch on the right of the flow circulation, which looks really similar if you look at it in details. And so here is a Puget Sound picture of an estuarine circulation driven by those rivers in Puget Sound. Okay, so I'm not going to say by any means my group's the only group that's now looking at this as a system. There's at least 4 complete 3-dimensional models of the Salish Sea from different groups. But now with these models, we're starting to look at the whole thing more as a system. And so I'm going to talk from my point of view, from my model, which is Salish Seacast. It's a NEMO 3.6 configuration, which is a primitive equation model. So we're starting from the Navier-Stokes. It's deterministic, not a statistical or machine learning model. It's fully baroclinic. Our grid spacing is about 0.5 kilometer by 0.5 kilometer. The vertical grid spacing is higher near the surface, like closer together near the surface, and then bigger at depth. And that's because we run this model coupled to biology, and we really want to look at the biology at the surface, but I'm not going to talk about any of that today. And it has a full turbulence model in it. All these runs were done based on our most recent version, either directly from the real-time model or running a clone of the model for the rivers. Okay, so my 3 co-authors here, which you didn't get the slide, but this is Cassidy Donaldson, Jose Valente, and Cameron Stang, and they are students or past students of mine. So Cassidy Donaldson put dye in the rivers so she could see where the river water went. So she marked the Fraser River water. She marked 10 other small and medium-sized rivers, and then any other of the rivers that has water coming in went into the other category and got the same dye for all of them. There are over 150 river mouths in the model. Jose is part of a microplastics research group, and that group is focusing on polyester microfibers, which are the fibers that come off your fleeces. So they primarily come off in laundry. One of the interesting things about polyester microfibers is they are dense. Most of the microplastics research has been done on buoyant particles, buoyant plastics, but these are sinking plastics. And so he studied them using particle tracking, using a Lagrangian particle tracking model called ocean parcels. Cameron Stang looked at actually the exchange flux, the actual water moving through the system. She did it in a quantitative way using a Lagrangian package called Ariane. And so that looks at a flux between two transects, and she looked at a season, and we're going to look from her seasonal average over 4 years. Okay, so let's start with the Fraser River water. So what I've done here is on the left is just the domain of the model, and I've turned it so that I use the space on the screen better. So we've actually turned it 29 degrees in order so you can see it, but I think you can still see Vancouver Island. And you can see the bathymetry there. Then in the center panel, I am showing you the flux of, the meters of Fraser River water on average that's in that particular column of water. Okay, and people do this from observations by trying to find a reference lane. We don't have to do that. We have dye. So we actually know how many meters of water there is. And so there's up to 20 meters of water in places there. I'm just going to take a second to get rid of that thing at the bottom because I want you to see Puget Sound. There we go, because Puget Sound is one of the big parts of this story. So actually down in Puget Sound, there's about 3 meters of water. And so what we're seeing here is the meters of water for Fraser River water is very similar to the bathymetry. And that's just suggesting that after all the spin up and everything, and on average, the Fraser River water is well mixed in this system. I do want you to pop over to the last one, which is actually average concentration. And there you can see, yes, the average concentration is highest around the Fraser River. So this isn't totally crazy, but we are seeing really strong mixing through the system. And so, yeah, where the water's deeper is where there's more fresh water when you integrate it over the whole system. Okay, and so this is another way to look at it. And so what Cassidy did was pull out boxes, and you can see various boxes and how much the average fresh water is there. The top one is the inlets up at the top. Those fjords are very deep, and so we're just seeing that depth effect. The next one down, the yellowy one, is the one that's closest to the Fraser River, so it has lots. And then right down at the bottom, there's a blue line that's fairly smooth. And that is the amount of water in Puget Sound. And so on average, Puget Sound has about 1.5 meters of Fraser water in it. Okay, and so this sketch is Cassidy's sketch, and this is what's happening. You'll notice that line was very smooth compared to the others, and that's because it's double mixed. So first of all, that Fraser River water was mixed in that mixing region in the Gulf Islands, and now it has to get Puget Sound. So it's going over yet another mixing region. And so here we can see Admiralty Inlet and the sill at Admiralty Inlet. We have the Pacific water coming in at the bottom. And then in the next layer up, we have this mixed Fraser River sog water. And then right at the surface is the estuarine flow from Puget Sound going out. And so what's coming in from the Fraser River is going in and forming the Puget Sound intermediate water. That's 3 minutes to the end or 3 minutes to stop talking? Okay, good. I'm doing fine then. Otherwise, it was going to be Panic City. Okay, so the intermediate water in Puget Sound is formed from the Fraser River water. And notice that only the surface water is going out, only the Puget Sound River water is going out. So now let's take a look at those plastics. And so Jose modeled the plastics based on the population centers. And if you look on the far left, you can see those population centers. We see very strongly illustrated Vancouver, also Seattle, Tacoma. In the middle is the sedimentation, like how much is on the bottom. And remember, these particles are sinking. They basically sink to the bottom, even in the deepest water, in about 16 hours. We actually like them to be, we let them be resuspended as well. And so that's why that's not the whole story, but you do see a lot sedimented right away. And so what we can see is the strongest concentrations in sedimentation are close to those sources. But the interesting figure is the figure on the far right, and those transects have little red arrows on them, and they are showing you the flux of particles. And what's really interesting is the flux of particles is into Puget Sound. Puget Sound is an enormous source of particles. Like, there's a lot of people living there, but actually the net flux is into Puget Sound. Similarly, the net flux is into the Strait of Georgia from the south, even though Vancouver is a much, much bigger population center than Victoria. What's going on? Well, if we look at those thalwigs again, we can really see this. So first of all, the Puget Sound thalwig there, we can see enormous source. And that source is trapped in the bottom because it's the surface water that goes out, not the intermediate water. And these particles just can't get into the surface water because as soon as they get mixed up off the bottom, they're still sinking. And so they're trapped in that bottom water. And so we can see the same thing in the Strait of Georgia. And so we can add Jose's particles to Cassidy's diagram. And there they are stuck in the bottom in this intermediate layer, and they can't get out. And so we have dense particle trapping. And I think this is just a slow figure, but maybe not. Well, this doesn't look good. Oh, there we go. Okay, we can do this one. This is good. Okay, so this is now looking at the exchange fluxes. And so we have the winter versus the summer. The fluxes are stronger in the summer. But what's really interesting here is looking at the three different channels that the flow can go through. And we see that the Haro Strait, which is the one furthest on the west, has the most flux. But we also have a strong flux through Rosario Strait to the south only. If we look just at the fluxes that go from Puget Sound to the Strait of Georgia or vice versa, we see that the flux from the Strait of Georgia south to Puget Sound is in Rosario Strait and is focused near the surface, whereas the flux from Puget Sound to the north is in Haro Strait and is deep. And I'll just note that this is opposite to what you'd say from the Coriolis force. Okay, so there are details, and I think I'm running out of time, right? Yes. So you'll have to come back to me, but all this stuff is going to be available, and I'll just finish with my conclusions. So dissolved quantities are well dispersed throughout the whole system. Dense particles, however, can be trapped in the deep basin. The mean estuarine flow plus mixing explains the patterns we see. Even though we've got strong tides here and we have strong wind-driven currents, it's the mean estuarine flow that actually is determining these long-term patterns. U.S. water does travel north at depth through Haro Strait, and Canadian water does travel south near the surface in Rosario Strait.
Thank you. As a function of time, I think we should move on. I'm going to actually pass the coordinating duties to you now, Susan.
Right.
Sorry.
I don't get to go away. Okay, so our next talk is online, and good. I was about to say, what's that? What's this? And so as our great volunteer brings up the slides, we are now going to move to another session that was added into this section. And so this is now starting to look at using statistical models to downscale oceanographic and atmospheric work. And so we have 3 talks. Our first talk is from Al Herman.
Oh, so
Pardon? Yeah, but he goes by Al.
oh, okay. Yeah. Sorry about that.
Yeah, it is Albert Herman on the sheet.
Testing, testing.
Yep.
Can you hear?
Yes, we can hear you.
Excellent. Okay.
We
Let's
can hear
see.
you. And now we would like
Excellent.
to see your slides full screen.
Okay, I think I can do that. How does that look? Is that good? Is it showing up now? Hello?
Yes, just one sec.
Okay.
Can you try turning off the broadcast sound on your own computer, because we're getting Susan twice.
I don't have any broadcast sound on my own computer. I just am using headphones.
Okay, we'll just hope it doesn't come back again. It hasn't yet. We're just trying to get your screen full screen on our screen. I don't think it's anything on your end.
Okay.
Still working.
Okay.
So when you open that, just mute it. Okay, that's what's giving the feedback. This one? Speaker? Or should it go? Get him to speak.
Okay, Al, I think we're ready for you to go ahead, please.
All right. I will go then. All right. Greetings from Seattle. I'll be talking about the use of machine learning-based emulators in downscaling for regional modeling. And I'll start by talking a bit about fisheries management strategy evaluation, very briefly describe some of the models being used here, talk a bit about empirical orthogonal functions as a dimensional reduction method and their pros and their cons, then talk about the machine learning method used here, and its application in hindcasting, sensitivity analysis, and climate projections. So this is a nice figure by Kirsten Holzman. And the idea here is to illustrate how we would like to be able to make a lot of projections of possible futures using different global models, downscale them to a region. For instance, here's the Bering Sea shown. And in this particular case, the Regional Ocean Modeling System. That can be used to generate a regional, finer scale projections of aspects of the Bering Sea of interest to fisheries managers, like the so-called cold pool, big blob of cold water that appears most years on the Bering Sea shelf, and the biomass of zooplankton that serve as food for the fish. That output is then fed into fisheries models, and those can be subjected to a variety of possible management scenarios. The expensive part, and let's see, I think is my pointer working? I think it is. Okay, I will assume that it is.
And we can't see your pointer.
Oh, you cannot. Okay. Well, I will just describe verbally then. Yeah, the thing that marked ROMS NPZ, that's the really expensive part of this whole process. It can be very expensive to do that regional downscaling. Have to use much denser grids, much finer time steps than the global models. So that can be the real sticking point. So if you could develop a compact surrogate, which does most of what the dynamically downscaling model does, you'd be ahead of the game. You might be able to then generate a much larger ensemble of projections of the future, which would be of more value in this management strategy evaluation. Just as with weather predictions, it's good to have a big ensemble so you can say the probability of such and such happening is this much. You need an ensemble to be able to do that. If you have such a compact surrogate, you might also be able to do sensitivity experiments where you vary the forcings or the parameters and look at the response. That by itself could be of great value. So what we're focusing on here is the use of machine learning to construct a 3D surrogate, also known as an emulator for a regional model. One of the examples shown here will be the MOM6 model for the Northeast Pacific. Now, this is purely for entertainment value. I am old enough to be a child of the 60s who dealt with electronics chock full of vacuum tubes back in the day. And one of the nice things about dealing with analog equipment of that sort was the sort of instant gratification. You could spin a dial and immediately get a response. It would be wonderful if machine learning gets so sophisticated so fast that we can be spinning dials again and looking at sensitivities of our ocean models in that sort of interactive way. Now, over the decades, EOFs have been tremendously popular in oceanography. I'm sure everybody in the room knows this. They allow a complete reconstruction of the data. They can show the dominant spatial patterns. They immediately give you orthogonal spatial and temporal modes. That's a great advantage. On the other hand, it can be a disadvantage. The restriction, the EOF insistence on orthogonal spatial and temporal modes may obscure some simple signals that don't completely obey that. Fourier decomposition may in fact be preferable in some cases. And the smaller scale chaotic features in your field aren't going to be well captured. They're going to be somewhere down in the rubble of the higher modes. There are other methods for dimensional reduction for sure, and if you open any machine learning textbook these days, you'll find dozens of them. EOFs, which are really just principal components, are just one such dimensional reduction method. Now, I suggested in the abstract for this talk that one of the downfalls of EOFs is they have a hard time representing propagating signals, but you can actually represent propagating signals with standard EOFs. And that's due to the trig identity shown on the lower part of the slide relating propagating sine wave to where basically standing modes, sines and cosines in space and time separately. So those then become your spatial modes and your temporal modes in the EOF decomposition. So you can in fact represent propagating signals with EOFs, and because you're just doing singular value decomposition on a matrix, you can rearrange the rows of that matrix and you'll get the same answer, basically. The singular value decomposition doesn't really care how things are arranged in space. So you could represent a signal with a variable phase speed, with some very tortuous spatial path, using standard EOFs. It can in fact capture those. Now, the whole idea with dimensional reduction is to take, let's say in oceanography, to take a huge collection of time series and reduce it to a much smaller set. If you have that smaller set of forcing time series and response time series, let us say, you can use a technique like a recurrent neural network in machine learning to relate the forcing time series to the response time series as they both progress through time. A variant of recurrent neural network is called the long short-term memory network, and that retains information about the long-term behavior of the time series, as well as the short-term things that happened really recently. And as it goes, it learns to remember certain things and to forget other things. It becomes a very efficient way of dealing with time series where the past influences the present in some way that you don't necessarily know at the start. For example, the ocean has lots of memory of past atmospheric events, serves as a low-pass filter for a lot of things. LSTM can help you capture that. So what we've tried thus far is using LSTM. If you look at that top broad white arrow, that's the MOM6 or the ROM's dynamical downscaling that gets you from the forcing variables applied to the regional model to the response. And that response, of course, includes multiple oceanographic variables. You can calculate EOFs for each of those variables in the forcing and the time series, what oceanographers usually call the principal components associated with them. You can do the same thing on the regional response, get the regional ocean EOFs and the time series associated with them. Note those EOFs can be three-dimensional. You don't have to just do say surface and bottom properties or properties at certain levels. You can do the full 3D field because it's just singular value decomposition. It can be any arbitrary collection of time series. Now you've got your dimensionally reduced sets of time series. You can train a machine learning model to relate that one set of time series to the other set of time series. There's some details on the bottom, but I will allude to those later. Now that you've trained the model, you can feed new sets of forcings, project them onto the EOFs that you calculated previously in the training, gives you a new set of time series, which you put into your trained model, and that gives you a new set of responses. Put those together with your regional ocean EOFs, and you've got your new regional response. In machine learning terms here, we're using principal component analysis as the encoder and the decoder bracketing the long short-term memory recurrent neural network. Now, you don't have to use machine learning. You can use this sort of approach in a hybrid dynamical statistical downscaling. This was an example where we did that EOF dimensional reduction of the forcing and the response, and then used an additional principal component analysis to relate the forcing and the response. We could have used multivariate linear regression as an alternative. But this gave us a way of expanding our ensemble trained on half a dozen different realizations to something including more like 30 realizations. And it gave us a sense of projected patterns of euphosids, that is, fewer euphosids in the future, what the spatial pattern of that was going to be, integrated over an ensemble of 30 rather than our original ensemble, which was much smaller.
Time to summarize. 3 minutes left
Okay.
to the speaker.
All right. Let's see. The machine learning reduces the time from 200 CPU days down to 1 CPU second. So that's a big advantage. The method can be applied. The blue line is what's observed from dynamical downscaling. Red is from the emulator. Good match, but some divergence later on. Bottom temperature is actually well captured by this method. The training phase, the first few decades, the last couple of decades for testing. So we are able to reconstruct a time and depth pattern of temperatures on the southeastern Bering Sea shelf with some discrepancies. You can use this for sensitivity testing where you alternatively turn off different, hold on, there we go. Where you alternatively turn off different forcing elements. And you can use it to expand your ensemble. This was just another example. So they do show promise as fast emulators. They can capture the broad scale responses, and getting the smaller scale features is a whole lot trickier. In the future, we may be trying some things with separating out the broad scale and the fine scale features first before applying the machine learning methods. Another way people in machine learning typically do that is by using smaller patches of the full domain. That's a pretty standard thing in image recognition. And you could, of course, apply these methods to the raw output without using EOFs or dimensional reduction whatsoever. So I'll stop there. Thank you.
Thanks very much, Al. And due to time, we're going to just have to move directly on, I think. And so our next speaker is also remote, and that is a talk from Rick Danielson, a neural network remapping of climate model projections and thermal tolerance in Eastern Canadian marine protected area species. I'd like to remind everybody we are going to go into lunch, but they didn't run out of food, so don't worry. We'll be fine.
Can you hear me?
Yes, we can hear you, Rick.
Okay. Can you see this?
We're still working on getting the slides up here, but it looks good. Okay, I think we have your slides up and everything, so off you go.
All right, thanks. This is a presentation from a team of people on the East Coast Bedford Institute, and sort of to put it in context of the other talks, we're looking at a much simpler approach to parameterizing the historical relationship between the CMIT models that are available in numerous ensembles of multiple simulations to a single historical reanalysis of a few ocean temperature variables, ocean variables, including temperature, but salinity, um, surface and bottom, and so on. Again, the neural network approach is very simple, and I think that's what we are, how we're approaching the modeling this statistical modeling aspect is by starting with the simpler. So to be complementary to the more advanced approaches we want to explore later, we need to teach ourselves what we're parameterizing and how. So we think that we are. I'm listing basically the conclusions. So we're trying to map with precision. That's one of our goals, and that means we want to reduce bias and variance among CMOS variables. So reducing it towards Laurie's reanalysis. We want to keep the CMOS model trends, and we want better resolution in space than the CMOS models are giving us at the moment. And I'll show you what I mean by that. And if we can get that, we can look at some of the tolerance limits that Mike Casey was showing earlier projected into the future. And so we are focusing on a couple of the marine protected areas that Mike showed, as well as some in Banques Americaines and Muscat estuary. Some of the very smaller, shallower marine protected areas are also of interest here. So yeah, and the code is online. Just for background, the CMOS models are these are the listed on the right of the CMOS model. The CMOS models of which we are only taking one ensemble, and each model has a trend that allows us to refer to these models as warm or not so warm in their effective climate sensitivity. So a hypothetical quantity that describes in some stable sense what these models, how sensitive these models are to the forcing that is given to them. But the local trends can be different. And again, we're taking Glory's 12, which is a 12-degree resolution, so it's nominally eddy permitting or resolving, and for the optometric period, where the assimilation was done with the reduced photocommentary. Here is, so our process is then to take these model ensemble numbers and do a monthly, or take the monthly average of them, do a simple additive bias reduction, again, not impacting the trends or anything, and then do an average for the MPA. Here I'm showing the belly MPA with an average depth of roughly a kilometer, but varying in quite a bit from almost 3 kilometers to only a few hundred meters. And then for that average, both of, say, surface temperature or bottom temperature, taking an annual average and then plotting the trend. And when we compare the variations among the models for these annual averages across time, we see a lot of variability in the max and min models are the ones at the ends of the bars, I guess what I call the lines, and then the shading in black is the standard deviation. And you can see that there's also this difference between the Laurie's mean and the mean for the 22 models. And so we want to try and address that a little bit. The neural network, again, is very simple, and it's applied point-wise. So it's not a convolutional network, it's just a feed-forward network that's applied at each grid point. In having interpolated the CMOS model data to the Glory's grid, we're then taking basically monthly data and centered 1 year average of centered on that month, and then a multi-year average for that particular month, both on input and output in the training. So this is for the training is again for the historical period, and so we get one, effectively our output is one neural network for every model, variable, and grid box. And yeah, we're going to apply that going future. I should say that we're not, there's one caveat here, which is that the monthly data is PDF matched, or it's resorted effectively. So to allow the training to see extremes in at the simultaneous extremes in the input and the output. So we don't even need to worry about the evolution of CMIP models relative to what actually happened in history, because these models, the CMIP models, aren't assimilative models, so they just follow their own evolution. So there's no need to coordinate the evolution of the two historical data sets. But it is important just to show the neural network the extremes and the range. And that's actually an old technique that was developed by Felix and Chaloner in '94. So we've reused it in another project, and we found that training to be productive here. So this is the result. You can see a little bit of a reduction in the variance among the models, among the 22 model estimates of the trends, and a collapse toward, in the historical period, as expected, a collapse towards the glories average in the data. So we're just inserting this neural network step in our processing chain, and we get what we want. So if we go to St. Anne's Bank, also something that Mike was showing earlier, and I flip back and forth, you can see a reduction in the variance and nominally this bias or difference in the two estimates of the 6 variables that we're interested in. That's the initial variance among the models, and this is the variance after the calibration. We also want some spatial variability. So just as a key to how we're going to view the output of the models having trained the neural network with these individual grid points. On the left we have glories, and on the right we have two in columns B and C we have these two 20-year periods of CMIP model averages of in this case bottom temperature in the gully again, and between glories and CMIP we have a difference for the 20-year period at the beginning of the century, and then on the far right we have the trend in CMIP. So that's how we look at this plot, showing for each individual model what we start out with is a difference between CMIP and glories. So basically, if we're looking at the CMIP minus glories difference, we see these large differences in the initial time of the century, and then relatively small differences at the end of between the CMIP in the trend in the CMIP models. But we want to keep that trend, that 2090 minus 2010 is the period of the difference, the midpoint years. Want to keep the trends in the CMIP data. So if I move forward, you can see that we're reducing, as we'd like, we're reducing the difference in CMIP and glories, but if I flip back and forth, I don't know if this is going to show up easily on a virtual presentation, but flipping back and forth, we're reducing the CMIP minus glories differences, but we're keeping the trends more or less in surface temperature, again for the gully, and then also for bottom temperature. It's actually a little harder because, as I say, the gully is 1 MPa that covers this vast range in depth. And the CMIP models also have trouble representing that range. And if we move forward, we're kind of seeing residual effects of that difficulty in representation in CMOS, but we definitely see some patterns that are more like the Glory's representation. And again, we roughly keep the trend. So the conclusions here are basically that we are getting better precision. We're not sure about accuracy. We keep the trends more or less, and we get some better spatial resolution within the MPA. So we can then look at some of the tolerance limit changes projected by the CMOS models. So if there's time, I guess we can just look briefly at the number of species among the count in species for the different MPAs. This is the number of species that would reach the tolerance limit on the high end. So if the temperature was getting too hot for them, then we see these dramatic changes in the species that are presently expected or predicted to be in the MPA regions, but which would not be predicted to be there later. However, if we then insert our calibration, we get a reduction in that number, which presumably...
Time to wrap up, 3 minutes to the next talk.
Yeah, good. Well, I think I'm basically done. One other comment on precision accuracy, since we're trying to understand what these simple models are doing, we would cite some of the work that's already going on with GCMs to try and address the opportunity that calibration presents in updating the models. And I think we do have insight. Sort of a bias question provides a view of the internal coupling. And while we wouldn't want to disrupt the model, the internal balances and conservations in any significant way, the opportunity may exist at the interface of these models that GCMs are composed of, and that may be the place to look. Anyway, I'll stop there.
Thank you, Rick. Again, in the essence of time, I think we're going to move directly on to the last talk. I please ask everyone to reach out to Rick and Al with any questions they have. I know they'd be happy to continue the discussion, but due to everything that's been happening, including our problems with technology, I think we need to move on. So the last talk of this session is by Amber Holtzworth, who is actually the lead convener of this small section. And she's going to talk about statistical downscaling for the Northeastern Pacific Ocean. Amber, can you say something? Amber, we're not hearing you. Amber, we can see your slides, which unlike the previous two talks, took the longest to go, but we still can't hear you. Okay. Amber, if you would like to call Natasha, we can do it through the phone. This is where the microphone goes down.
Okay, Amber, can you try and say something?
Hi, can you hear me?
Yes. Okay, I'll turn you up. Yeah, you can go ahead.
Perfect. Thank you guys so much for sticking around for this last talk of the session. I can hear myself, so it's a little bit strange. Okay, so I entitled this talk Statistical Downscaling for the Pacific Ocean, but really this group starting with Pacific Ocean examples, and will actually be a Canada-wide working group. So hopefully I have something nice and light and fun for you for before lunch. So I'm going to tell you about why we need statistical downscaling. Then I'm going to tell you about the autumn 2024 meeting that we have, and I'm going to then finish up with some talk about the activities that we have planned in 2025. So first of all, why do we need downscaling at all? Well, downscaling plays a critical role in providing local climate information, which supports informed decision making. So when we run models of the climate system, they are run necessarily on the globe. And so this is relatively coarse because we have computational constraints. And so we use dynamical downscaling for these global models, and we can downscale them dynamically with our regional models by forcing them with the coarse models at their boundaries. But there's another method called statistical downscaling, which is a bit more computationally efficient. It isn't as reliable as dynamical downscaling simply because with dynamical downscaling, we actually resolve the 3D equations of motion, the Navier-Stokes equation. We have some perturbations which maybe are less reliable, but generally we think it's quite reliable. It's not that statistical downscaling isn't reliable, but we just have to be a little bit careful about an issue called non-stationarity. And so this is really just the idea that we map the relationship between the large and small scale in our training data set. And then when we apply it to a different data set, if it's out of the distribution of our training set, we can run into issues. So what kind of methods are we talking about here? Here we're talking about statistical methods like linear regression and machine learning methods all the way up to really deep learning methods. And so you can see here this nice diagram from HOPS 2022. It shows, machine learning and where it fits into artificial intelligence. Essentially, machine learning means that we have an algorithm that's learning a task from the data without being explicitly programmed for that task. And so there's a wide range of techniques that we can use for statistical downscaling. Statistical methods can allow us to extend existing high-resolution model hindcasts to different time periods, both into the future and into the past. And so we might want to do historical reconstructions. For example, Pacific salmon has data that goes back to the 1950s, but we don't have high-resolution model data to match with it. There's also probabilistic projections of future climate, which I'm going to tell you a little bit more about, and seasonal forecasts, which are increasingly needed. They're working at CCCMA to downscale the global seasonal forecast to a higher resolution, which we could then downscale to even higher resolution by leveraging some of our high resolution models. So I wanted to show you an example of some of the work that we did over the last 5 years, dynamically downscaling for the Salish Sea. You see Natasha and Eva Nagy are co-authors there, along with a bunch of other folks. Some of them are in the room. And we started with the NEP36 canoe climate projection with 2 scenarios. And then you see we used that to force the wharf atmosphere model at the sea surface temperature. And we also used the outputs from that to force the Salish seacast model at its open boundaries. So we downscaled the atmosphere through a nested subdomain to 3 kilometers at the internet, which we then used to drive the seacast. This is a lot of work, a lot of model development, tons of people involved, over 100 terabytes of data, and I haven't even quantified the amount of computing resources. And here we have projections from one global climate model with 2 scenarios for 2 time periods, which is incredibly useful, but it doesn't have the bounds on uncertainty that a risk-averse decision maker might want to have. And so we can use statistical methods to leverage the many high-resolution models that DFO currently develops. Here's just a smattering of examples from the Pacific of different high-resolution models. Particularly useful for the really high-resolution models you see here, which can be difficult to run for the 30 years required for climate projection. And so to try to advance the science of statistical downscaling for the ocean, I organized a working group meeting at the University of Victoria in collaboration with Adam Monahan. And we invited attendees from atmospheric sciences, computer science, climate science, machine learning, mathematics, ocean sciences, biochemistry, statistics, ecology, and maybe other things I didn't include. And the idea was that the atmospheric scientists are sort of ahead of us in doing statistical downscaling. However, the ocean may be more complicated. And so we really got everyone together to start to think about this. We have written a report, which will be released soon. We formed an unofficial working group, and we're working on community engagement through a Google group, as well as having a Git page, and this talk here right now, as well as some planned future sessions at Ocean Sciences 2026. Key messages that came out of that group were that there's a strong need and desire for community collaboration. Here I put transdisciplinary, and I use that word because it's not just that we come together and sort of stay in our own lanes and provide advice. Instead, we're trying to work together to break down barriers and come up with something new. And so we talked a lot about application-specific approaches. We really need to understand the specific problems to reduce the size of it and decide what method we should use. We talked a lot about how statistical downscaling can complement dynamical downscaling to enhance predictions and projections. It reduces computational costs, addresses uncertainties, but we need to do more research to confirm reliability, thinking again about extrapolating beyond training data. Because of course we know, climate, for example, is inherently non-stationary with warmer temperatures expected in the future. Something I'm really excited about are hackathons to focus on really specific problems. And so the idea here is that the choice of methods should really be grounded in the specifics of the problem rather than in the vacuum of philosophical discourse. I took that quote from Hubb's paper where she's talking about the difference between traditional statistics and AI, but I think it applies to machine learning methods in general. So the idea here is that we're going to gather a group of interdisciplinary experts, clearly define a problem, process data in advance and identify the computing resources. Then we're going to think about the logistics. Maybe we'll have each team look at a different method and then figure out a metric for success. The idea is to produce publishable data sets, right? Because everybody involved here is a technical expert. We should be able to get something, really usable and useful for the community out of it. And of course, we want to have fun and learn a lot about machine learning and statistics. And so the two hackathons we're planning are Line P, which is an historical reconstruction. I'm going to tell you a little bit more about it. And then Burrard Inlet, which is an example of climate projections in small craft harbors. And so the timeline here is that we spend few months planning, try to have the Line P hackathon in September. It'll probably be virtual. And then we'll have another few months to plan for Burrard Inlet, and then hopefully have an in-person hackathon in early January. And so hackathon 1 is about filling in the gaps in Line P. If you're not familiar with Line P, it's actually one of the longest time series in the ocean. You can see the line here off of West Coast Vancouver Island. It has ship-based sampling starting at Station Papa in 1956 and officially began in 1959. The major stations have temperature, salinity, oxygen, DIC, and alkalinity for some of the years. The minor stations have temperature, salinity, and maybe oxygen for some of the years, and might be sampled less frequently. There's several regional models that are also available for this region. And so with this, we're going to try to generate time series of temperature, salinity, DIC, and oxygen for all stations along the line, which is going to mean filling in temporally as well as spatially. Hackathon 2 is about climate projections for small craft harbors. Inlet, because we have a relatively large amount of data for that inlet. We have a lot of CTDs, throttle data, drifters, tide gauges, and river observations. There are also 2 high-resolution port models that were developed under the Oceans Protection Plan for navigation and emergency response. And that's South Salish C-150 and Vancouver Harbor 20, which you can see in the map on the side. We also have regional ocean models with hindcast and future projections. And potentially we can infer some of the stationarity issues from these larger scale models. This is a particularly challenging problem, but I think we can make some headway on it if we put our heads together. And so that's what I really have for you today. So I've just told you about the statistical downscaling for the ocean working group. The idea is to advance the science and application of statistical downscaling for the ocean. We are focusing on specific examples. This is a step towards answering really vexing problems, helps us understand which method works for which purpose. It's about establishing a network of practitioners involving transdisciplinary collaboration And, we're thinking about writing a worst practices guide. Like, maybe we can't tell you the best thing to do, but through all this effort, we can probably tell you what you shouldn't do. And we want to share tools, data sets, and findings to avoid duplication of efforts. That's a big tenet of this group is we don't want to just do this and then have the tools for ourselves. We want to enable everyone to do this. And we're planning a session at Ocean Sciences meeting 2026, so look out for that. If all this sounds really cool to you and you want to get involved, just reach out to me and be happy to include you in the group. And thanks so much for your time.
As Amber finished right on time, I will take a quick question, if anyone has one. If not, I'll let this session wind up because I know lunch is waiting for us, but I would encourage you to talk to Adam or talk to me if you want to be involved in this. I think hackathons are a great way to learn, and I encourage you to think about joining us. Total understanding of the Pacific is not necessary. There are lots of us who will be part of it that know that. But any statistical stuff will be good. Thank you very much for coming to this session, and thank you so much for staying. Thanks again to all the speakers, and thanks to other people who struggled with our come back to this room after lunch for stuff on models.
No problem.